abstract algebra fans. Here we are in our live stream for the hour. We're going to be talking about permutations and the properties of symmetric groups. Really my goal for our time together today in the stream over the next hour is that I'd like for us to get a chance to practice a few different types of reasoning problems involving permutations in the symmetric group. Let me talk a little bit about the goals while we're getting everything set here and people are arriving for the live stream. So the first thing I want to do is I want to reinforce a process we've been talking a lot about in class, and that is how do you simplify permutations. And specifically, I want to sort of tackle a more intricate problem. I assigned a couple in the homework that had kind of a lot going on. So I want to talk a little bit about a couple of shortcuts for taking powers of cycles as well as powers of inverses of cycles. So we'll get some more practice with that simplification process today. Part two is I want to take a deeper dive into the orders of permutations. So not just the order of a cycle, but the order of a permutation that's comprised of a product of disjoint cycles. So how do we discover the order, and then how do we use that principle to be able to somehow classify as completely as we can what are all of the different orders of permutations that we may have in a symmetric group. So that's the sort of second bit of what I want to do together today. Whoops, sorry, chat window. And then the third is I want us to think about the structure, the subgroup structure of the symmetric group. And in particular, we're going to think some about the alternating group, which is kind of the premier subgroup inside of the symmetric group. But then also we'll do a problem where we have to assess whether a certain subset of the alternating group is a subgroup or not. So first, I just want to comment about the thing I said a minute ago about the alternating group being somehow the premier subgroup inside of the symmetric group. So here's how it works. So you have the symmetric group on three symbols, which, as we've seen, but we're not always thinking about, but this is a good time to remind you, it's actually the same as the symmetric group of a triangle. Sorry, the group of symmetries of an equilateral triangle, D3. D3 and S3 are the same group, and the sense in which I'm using the word the same is still something we haven't concretely defined this semester, but the good news is we will next chapter. In chapter 6, we're finally going to gain the footing to be able to prove that two groups are the same. But leaving that aside for a minute, one of the nice things about the symmetric groups is that there's a nice inclusion that each has in the next. So for example, every way in which I can permute three symbols, I can also find those permutations of three symbols inside of, as a subset of, the permutations on four symbols. How do I do that? Well, forget one of the symbols in S4 and just permute the ones that are left, and those will be described by the elements of S3. So S3 can be realized as a subgroup of S4. It can actually be done in four different ways, depending on which one of these four symbols I decide to forget in order to get back to S3. So S3 is a subgroup of S4. Can be realized as a subgroup of S4. S4 is also the same as a subgroup of S5, which is the same as a subgroup of S6. It goes the other way also, right? That S2 is the same as a subgroup of S3, and so on and so on. So that's one of the nice things about the symmetric groups, is that as we add more symbols, we're not losing any structure along the way. All the permutation that we could do with fewer symbols, we can also do with those same fewer symbols in a higher level, at a higher number of n. But within the symmetric groups, there are also the alternating groups. And remember, the alternating groups are the groups of just the even permutations of n symbols. So these are just the permutations that can be written as a product of an even number of transpositions. So we were able to show that this was a subgroup of S3. And in a very real sense, I kind of think that this is the most important subgroup that the symmetric group has. It also happens to be what's called a maximal subgroup, because it's the biggest subgroup that Sn can possibly have, is An. And that's because An comprises fully half of the number of elements that Sn has. A couple of chapters later, we're going to develop some language around assessing the size of subgroups relative to their supergroup, their parent group. But one of the words we use is index. Index is just the ratio between the size of the order, let's use the right word, the order of the parent group and the order of its subgroup. And the index of the alternating group inside of the symmetric group is 2. And we say that because it has half as many elements as the large group does. But then the alternating groups, which are subgroups of the symmetric groups at every one of these levels. So A3 is a subgroup of S3, A4 is a subgroup of S4, A5 is a subgroup of S5, and so on. The alternating groups are also themselves subgroups of one another. So A1 is a subgroup of A2, which is a subgroup of A3, which is the same as a subgroup of A4, which is the same as a subgroup of A5, and so on, and so on. So this sort of ladder picture that we see here kind of gives us a way in which we can think about the symmetric groups and the alternating groups all at once, all together, as being one kind of big object, as opposed to thinking about each one of them by itself and on its own. So let's get going. If you have questions as we're going and you're watching live today, feel free to drop them in the Twitch chat, which is right there underneath us here. You'll see it in the video. Or you can also drop questions into Slack, into the Doctor's Office channel. I'm keeping an eye on both of them. If you have questions and you're watching live, feel free also to drop in after the fact and watch this. Again, of course, if you're watching right now and you're hearing me say that, you're already watching it once. But tell your friends in the class that if they're not watching it live, they can come watch it later on afterwards using the same link that you used to access this stream today. So let's move forward. So here's a problem that I'm sort of pulling out of a hat here. And let's tackle this together. Suppose that I have this product of disjoint cycles, and I'm going to think of them as being elements of S9. So inside the symmetric group on 9 symbols, I've got this product of the 3-cycle 167 and the 5-cycle 14825 with a power of -2, so we have to figure out what that means, and then 359 with a power of 2. Remember, of course, that anytime we write down permutations, we're going to understand what they mean using the contravariant ordering, right? That by writing down this set of 3 permutations in a row like this, what I mean is that this cycle here is acting first on the set of 9 elements that it's permuting, and then this cycle is acting next, and then this cycle at the end is acting last. So just bear that in mind, that anytime we read this, we have to read it in what I'm calling the contravariant order, reading from right to left. Again, we do that because we define permutations in terms of function composition. And function compositions are always read from right to left also, right? The f circle g, for example, is the function which applies g to its argument first, and then applies f to the result of the output of g. All right, so how are we going to figure out how to write this as a product of disjoint cycles? Well, the first principle, as it always is I'm just going to ask what happens to each one of my symbols, 1 through 9. To each symbol. And there are 9 symbols here just because I've said that this is an element of S9. So that's my roadmap, is I'm going to take each of my symbols 1 through 9 and then trace what happens to that symbol, sort of trace its path through all of the permutations that are acting upon it, again, from right to left as we read it in this composition. So let me keep score down here at the bottom of the screen. So I'm going to start by writing a big 1 in these parentheses, and then try and figure out what happens to 1. So where does it land after all this permutation happens? Where does 1 end up? So I'm going to go one permutation at a time, one cycle, at a time, and ask what's happening to the element 1, position 1, as each of these cycles does its thing. So first of all, 1, when the 359 cycle acts upon it, is not going to be changed at all. So if I keep score here, we're going to have no change for 1 when that first cycle acts. But when the second cycle acts, 1, and it's still in position 1 because this one didn't change it, 1 is going to be going to 4. But the problem is that we're not just doing this cycle once. We're actually doing it twice, but we're doing its inverse twice. So let me give you a shortcut for how to take powers of cycles and also powers of the inverses of cycles when we're simplifying the products, as we're doing today. So remember, first of all, that taking the inverse of a cycle is as simple as reading the cycle backwards. So we tend to read cycles from left to right. So we agree that a cycle is read from left to right. 1 goes to position 4, 4 goes to position 8, 8 goes to position 2, and so on and so on. And the inverse is what we get when we read the cycle from right to left instead. So when the inverse of this cycle acts on position 1, it's going to take a step to the left, which wraps it back around to the other end, and 1 will go to 5 in the inverse. But this is not just the inverse. This is the inverse applied twice. So what's the shortcut? The shortcut is that instead of taking 1 step forward or backward in this cycle, I'm going to take 2 steps. So when this 3 cycle is applied twice, I'm going to take 2 steps to the right in my cycle. So 3, for example, is going to go not to 5, but to 9 when this cycle acts twice. Here, because I'm doing the inverse twice, I'm going to be taking 2 steps to the left every time I apply this cycle. So where is 1 going to end up after this minus 2 power of this 5 cycle does its job? It's going to end up 2 steps to its left. It's like these are all sitting around a big round table. Everybody stands up from their chairs, and they move 2 seats over to the left. 1 seat lands me here, 2 seats lands me there. So after this minus 2nd power does its job, 1 ends up in position 2. First step to the left gets me to the 5. Second step to the left gets me to this 2. So 1 goes to 2 when this minus 2nd power of this 5 cycle acts. And then remember, the question then is, where does 2 go? Because this last permutation is going to act on whatever input it receives from the previous permutation. And when the previous permutation is done with 1, the output is 2. And that output becomes the input to my next permutation. So where does 2 go? Well, the 3 cycle 167 doesn't actually change 2 at all. And so 2 actually stays put. So the sum total here is that 1, position 1, doesn't move when this first cycle acts upon it. It then lands in position 2 when the second cycle acts on it. And then nothing happens to position 2 in the last permutation. So the net result is that 1 is going to land in position 2. So I'll put that down here as the next element in my cycle. And then we're just going to keep going. Anytime we write a cycle, the question we're asking ourselves is, where does this position then go? So now that I know that 1 goes to 2, the question is, where does 2 go in this product of cycles? So let me erase what's under here, and we can start asking that question again. So in my first cycle, the one at the end of the line here, 3, 5, 9, 2 is unchanged. I'm going to use the fancy word fixed here again. So nothing's happening to 2 in this permutation. Meanwhile, 2 is being changed by this middle permutation. And how? We're going to take 2 steps to the left, right? Because I'm applying the inverse of this cycle twice. So if I take 2 steps to the left, we find out that 2 ends up in position 4. And then again, the question is, when 4 becomes the input to this permutation, what happens to 4 in that case? But this is not changing 4 at all, so 4 is fixed. So the only place where 2 is being moved at all, the only action that's happening here, is in the middle, this permutation where 2 ends up getting moved to position 4. This doesn't change the 2 in the beginning, this doesn't change the 4 in the end. So the net result is that 2 goes to 4. And so where does 4 go? There's something almost soothing to me about chasing these permutations through. It just becomes, once you get the rhythm down, it's just like it's almost like a dance. 4, nothing happens in this first cycle. In the second cycle, 4 is going to end up taking 2 steps to the left, 1 step to the left, and then 2 steps to the left wraps me back around. So 4 goes to 5. And then 5, which is now the input to my third permutation, is not being changed by that third permutation. So the net result is that 4 goes to 5. Now where does 5 go? Make some room here again. In my first permutation, Now 5 is actually doing something, right? And since I'm applying this 3 cycle with a positive 2 exponent here, I'm going to take 2 steps to the right to figure out where 5 goes. So 5 is going to go 1 step, 2 steps, which wraps me back around to the beginning. 5 goes to 3 in that first cycle. Then where does 3 go? Well, 3 doesn't participate in this 5 cycle over here at all. So 3 stays put. And so 3 becomes the input to my last permutation in the line, which also doesn't change 3. So the net result is that 5 goes to 3. And we're rolling right along. Where does 3 go? I'm going to try to start speeding this up here. We're almost done. I take 2 steps to the right, and I find out that in the second power of this 3 cycle, 3 goes to 9. 3 goes to 9. And then 9 doesn't participate in this cycle, and it doesn't participate in that cycle. And so 3 goes to 9 at the end of the day, making 9 the next position in my finished cycle here, which is the product. Now where does 9 go? Take 2 steps to the right, 1 step, 2 steps. 9 goes to 5. And then 5 becomes the input here. This one I do want to keep score because there's going to be a lot happening. 9 goes to 5. And then 5 becomes the input here, for which I take 2 steps to the left. 1, 2, 5 goes to 8. And then 8 becomes the input in my last permutation. 8 is fixed. And so the net result is that 9 goes to 8. I'm building a really long cycle, it turns out here. Where does 8 go? Well, nothing happens to 8 in this first permutation in the line. So I'll just write here 8 is fixed. But then that means that 8 becomes the input for my second cycle, in which I take 2 steps to the left, 1, 2 steps. 8 goes to 1. And then 1 becomes the input for my last cycle, which acts only once. This is the first time this has had a chance to do anything. So finally, this 3 cycle gets to do something. And we take 1 step to the right, as we do in just a single cycle. 1 goes to 6. So this is the first example we've seen here, where all 3 of these permutations are actually doing something interesting, and not just fixing the input that they get. So ultimately, 8 goes to 6. Sorry, not every one. 8 was fixed here, but then 8 moved to 1, and over here 1 moved to 6. So ultimately, 8 ends up going to 6. And gosh, we've got to be almost done. So where does 6 go? Because now all but one of our symbols has shown up in my cycle. Where does 6 go? Nothing happens to 6 in this cycle over here. So I'll just write 6 is fixed, which means that 6 also becomes the input to the cycle in the middle, which is also not doing anything to 6. So 6 remains the input to my last permutation. My last permutation sends 6 to 7. Now, we'll glance at this cycle that I just wrote down and notice that we've written down every one of the symbols inside of S9. All 9 positions are represented here. But just to check our work, let's go through the last step of figuring out where 7 goes, just so that we know for sure that we've closed our cycle. Where does 7 go? Well, 7 is not changed by the first cycle in the line here. 7 is fixed. 7 is also fixed by the second cycle in the line. So the only cycle that does anything for 7 is this last one, in which 7 takes 1 step to its right, wraps back around to 1. And sure enough, what we hoped was going to be true is true, that 7 goes to 1, and therefore we can close our cycle. So there's the complete rendition of this problem. How do I simplify this product of powers of cycles? Really, the only new tactic that I'm sort of giving you here is how to, in a shortcut fashion, deal with powers of cycles. And we can think of a power as just telling me how many steps to the right that I want to take when this cycle is acting. So when I had a second power here, it means that instead of taking only 1 step to the right when I apply this 3 cycle, I'm going to end up taking 2 steps to the right. You might also notice, by the way, that taking 2 steps to the right in a 3 cycle is actually the same thing as taking 1 step to the left in a 3 cycle. Play around with it and you'll sort of see why, right? That 3, 5, 9, taking 1 step to the left would be a -1 exponent. And these two things are the same. 2 steps to the right around a table that 3 people are sitting a round table, is the same as one step to the left around that table. But let's think for a moment about why that makes sense. Why would the second power of this element be the same thing as the minus first power of this element? That actually tells me something about the order of 359. If I take and I multiply both sides of this equation by one more power of 359, turns out it doesn't matter if I do it on the right or the left. Let's just imagine that we're doing it on the left. Then what that gives me is on the left-hand side of my equation, 359 to the power 3. But on the right-hand side, I have this permutation multiplied by its inverse. I get the identity. Or if you're reading Gallien's book, it's sometimes written with an epsilon, which I think is kind of confusing, so I prefer to use the empty cycle as my identity permutation. But remember what this is telling me. This is telling me that this 3 cycle has order 3. After all, its third power gives me the identity permutation. If everything in this cycle takes 3 steps to the right, everything lands back where it started. For example, position 3, 3 steps to the right, 1, 2, wrap back around to 3. So we end up where we started. This is not groundbreaking. We already knew that K cycles had order K. But that, again, sort of gives me some reassurance on the strategy that we're using here to simplify powers. Let me take just 30 seconds and pause and ask, are there any questions that people would like to see addressed just for the moment? All right, then we are going to move on. So we've seen now how to simplify products of disjoint cycles, and also in particular how to contend with taking powers, both positive and negative integer powers. And a lot of that has to do with talking about the orders of elements inside of the symmetric group. So let's also look at this example. So I want kind of a really open-ended question here. I want us to take a few minutes to figure out, of all the elements inside of S6, the symmetric group on 6 symbols, how can we classify the orders of all of those elements? What orders are possible? After all, this is one of the most fundamental questions that we want to be able to ask and answer about a group in group theory, which is, tell me about the orders of the elements in this group. It's been a very powerful tool that we've had so far in comparing groups one to another to determine whether or not they are the same, for whatever that means. So how would it work for the symmetric group on 6 symbols? Now keep in mind, what I'm not asking you is what's the order of the group. Remember the difference between these two uses of the word order. The order of an element is how many powers of that element we have to take before it becomes the identity again. The order of a group is just a fancy word for how many elements does this group have. And we know, based on combinatorial principles, right, that the symmetric group on 6 symbols is the number of different ways to permute a set of 6 objects, and that's 6 factorial, which is a pretty big number. There's 720 elements inside of S6. So any strategy that we would employ here in which we would try to list all of them and figure out what their orders were, that's a bit brute force for me. If I tried to write out all 720 elements, it would take easily more than the rest of the time that we have together in the stream today. So I don't want to do that. I want to take a smarter approach. And the smarter approach that I want to take is powered by this formula that we saw in our lecture videos for this chapter. And it says that if I can express a permutation as a product of 2 disjoint cycles, so if sigma and tau are disjoint cycles, then we have this really handy formula for how to find the order of sigma tau. It's nothing more than the least common multiple of the order of sigma and the order of tau. So if I can express my permutation as a product of disjoint cycles, I can use this order formula to find the order of that product of disjoint cycles. And if I happen to be able to write the permutation as a product of 3 cycles or 4 different cycles or whatever, then I would just take the least common multiple of all the orders of those cycles. Right? This, by induction, if it works for 2, it's going to work for any finite number of disjoint cycles composed together. And so the least common multiples are the key to answering this question about what are the possible orders of elements inside of S6. So, if the question is about disjoint cycles, and we know every permutation can be expressed as a product of disjoint cycles, and we know that the order of a cycle is exactly the same thing as the length of that cycle. The order of a 3 cycle is 3. The order of a 6 cycle is 6. The order of a 9 cycle, which was the answer to our last question here, is 9. Right? We know the order of a k cycle is k. And we know that anytime I compose disjoint cycles, the order of their product is the least common multiple of those orders. That means that we can completely answer the question about the orders of elements by answering the question, what lengths of cycles are possible inside of S6? So here's how we'll arrange the work. Every element in S6 is going to be some way in which I can permute a set of 6 objects. Right? And so figuring out the cycle lengths, right, is going to tell me what I'm going to call a cycle type. And then we'll be able, from the lengths of the cycles that comprise this permutation, to figure out the order of those elements that have this cycle type. Because if this formula here is true, then the order of a permutation only depends on the cycle type. What lengths of cycles, what lengths of disjoint cycles is it made of? If we answer that question, then taking the least common multiple will tell me completely what the order of that element is. So I'm kind of talking around the question here. Let's look at one example. Let's suppose that I have a permutation which, when it acts upon these 6 symbols, maybe it does something to the first 4. So maybe it applies a 4 cycle to the first 4, and then it applies a 2 cycle to the last 2. So an example of a permutation that might do this would be 1, 6, 4, 3, composed with 2, 5. So this is one, what I call cycle type inside of the symmetric group on 6 symbols. A 4 cycle composed with a 2 cycle. So I'm going to call that cycle type 4 plus 2. So when I say 4 plus 2, what I mean is it's a 4 cycle composed with a 2 cycle. Notice that because disjoint cycles commute, I could also have called this 2 plus 4. I could have just moved this to the other side. So for this video, we'll just use the convention that when I write a cycle type, I'll write the lengths in decreasing order. So I'll write the 4 before the 2, for example. Okay, so that's the cycle type I'm talking about here. What would the order of this cycle be? Well, because these, what would the order of this permutation be that I get by composing these 2 cycles? Well, because these are disjoint cycles, the order formula applies. And so the order of this permutation is the least common multiple of the order of the first cycle and the order of the second cycle. But that's the same as the length of the first cycle and the length of the second cycle. So just to write this out completely once, it's going to be the least common multiple of 4 and 2. And the least common multiple of 4 and 2 is 4. So we conclude that this permutation is going to be a permutation of order 4. Before we move on, let's also, just for fun, assess whether or not this permutation is an even permutation or an odd permutation. And for this, remember that the key is that every cycle, every k cycle, can be expressed as a product of k minus 1 transpositions. And how many transpositions tells me whether or not a permutation is even or odd. So I know, for example, that this 4 cycle can be expressed as a product of 3 transpositions. And I actually don't care what those are right now. I just care how many there are. Meanwhile, my 2 cycle here is already a transposition. So in total, how many transpositions do I have in this permutation? I've got 3 of them coming from the 4 cycle, 1 of them coming from the 2 cycle, and so I have a total of 4 transpositions. And that tells me, therefore, it tells me that this permutation is an even permutation. So I'm just going to write here an E for even. And we've classified this cycle type. And what's really friendly about the symmetric group is, even though we have fully 720 elements in this group, it turns out that how these permutations behave is something that's defined entirely by their cycle type, at least how they behave with respect to themselves, right? The order is something that's constant across cycle types. Right? So every cycle that's a 4 cycle composed with a 2 cycle, every permutation that's a 4 cycle composed with a 2 cycle, is going to be an even permutation, and it's going to be an element of order 4 inside of our group. It turns out there's a lot of those. Right? We could do a different combinatorics problem to figure out how many elements there are of this cycle type. We won't do that in this video, but maybe that's a question that if you're taking combinatorics this semester, you could work a little bit more on that. There's also a lot of rich study and theory about symmetric groups that uses the theories of partitions to explain a lot of the properties that we're talking about right now. We may actually see why that is as we progress down through the rest of this chart here and figure out the orders of the rest of the elements inside of the symmetric group. So this is certainly not the only cycle type that we can have inside of S6. It turns out, and this too is a combinatorics question, it's about counting partitions of the number 6, that there are 11 different cycle types of elements inside of S6. So let's just sort of burn through these and try and list as many of them as we can. Probably the most obvious one that we didn't list here at the beginning is, what if I just have a permutation which is just a 6 cycle, which just takes all 6 of my symbols and permutes them in some way that makes a 6 cycle. So we call that cycle type the cycle type 6. And the order, well, because this is only a single cycle, the order is just the order of that cycle. It's order 6. Is that an even or an odd permutation? Well, it's a 6 cycle, and so it can be written as a product of 6 minus 1, 5 transpositions. And so that is an odd cycle type. It's an odd permutation. All of the 6 cycles inside of this group are odd permutations. Okay, let's keep going. What's another cycle type that we haven't looked at? Well, what if I have a 5 cycle? So if I have a 5 cycle inside of the symmetric group on 6 symbols, it must mean that the 6th element is being left alone. We could call this cycle type 5 plus 1 if we want to. But remember, a 1 cycle is the same thing as just the identity permutation. So if I wanted to, I could just call this cycle type just 5. But I think I won't. I think I'll call it 5 plus 1. Just to be sort of brutal about it. So it's a 5 cycle. That means that its order is 5 as an element of S6. And also that it can be expressed as a product of 5 minus 1, 4 transpositions. So all of my 5 cycles inside of S6 are going to be even permutations. All right, well, there's one more cycle type that we haven't seen yet that has a 4 cycle in it. My first cycle type had a 4 cycle composed with a 2 cycle. But what if I had a 4 cycle composed with 2 1 cycles? So a 4, a 1, and another 1. So I might call this cycle type 4 plus 1 plus 1. So in other words, this would just be a 4 cycle inside of S6 that does its thing on 4 of my symbols. But then the other 2 symbols are each living within a 1 cycle with themselves. And so they're just staying put. So all I get is really just a 4 cycle, and the order of a 4 cycle is going to be 4. Since a 4 cycle can be written as a product of 4 minus 1, 3 transpositions, that makes the 4 cycles odd permutations. All right. So we've exhausted everything that includes a 6 cycle in it, everything that includes a 5 cycle in it. Those are the only possibilities. Those that include a 4 cycle, we have 2 different ways of doing that. A 4 plus 2, so permute these 4 in a 4 cycle and these 2 in a 2 cycle. Or 4, 1, 1, which means permute these 4 in a 4 cycle, but each of these are staying put. So now we need to move down to those that contain a 3 cycle. So if I decide that I have a 3 cycle as part of my permutation, one option for the remaining 3 is I could put them into a 3 cycle also. I would call that cycle type 3 plus 3. What would be the order of a 3 plus 3 cycle? Well, it would be the least common multiple of 3 and 3. Well, least common multiple of any number with itself is going to be itself. So these are going to be elements of order 3. What would the order of, the parity, is it even or odd, a permutation that's a product of 2 3 cycles? Well, this 3 cycle would be a product of 2 transpositions. This one would be a product of 2 transpositions also. So sure enough, when I compose them together, I'd get 2 plus 2 transpositions. That'd be 4, making this an even permutation. So that's what happens with the 3 plus 3 cycles. But 3 plus 3 is not the only cycle type that includes a 3 cycle in it. I could instead have chosen to permute 2 out of these 3 and leave one of them fixed. If I did that, I'd get a cycle type that I would call 3 plus 2 plus 1. While I'm writing this, let me pause to say that this is a very long problem. And that's indicative of the fact that I'm probably not going to ask you to do something quite this extensive in the context of a quiz or the context of an exam. So don't be too concerned over how much time this is taking. I want us to talk through it because there's a lot that we haven't had a chance to really get into the weeds about when it comes to cycle types. And this is a really good way for us to acquaint ourselves with cycle types and how cycle types work. In particular, how they are determinative of the order of elements inside of a symmetric group. So here's a permutation that, let's say, for example, 1, 3, 4 composed with 2, 5, and then 6 stays in place, right? So that'd be a 3 plus 2 plus 1 cycle. And its order would then be the least common multiple of 3 and 2. But 3 and 2 are relatively prime, so their least common multiple is 6. So let me pause right here and just point out that there are, so far, we've seen 2 different types of elements inside of S6 that have order 6. There's the 6 cycles, but there's also the 3 plus 2 cycles, the product of a disjoint 3 cycle with 2 cycle. Same thing with order 4. We've seen 2 different types of elements that have order 4 inside S6. A 4 plus 2 cycle, but then also just a 4 cycle. Right? Those both have order 4. Finally, is this an even or an odd permutation? Well, the 3 cycle is going to be even. The 2 cycle here is odd. And when I compose even with odd, the result is odd. Okay, this is not the only cycle type that includes a 3 cycle. We can keep going. I could include a 3 cycle, and then I could decide to leave all 3 of these elements here fixed. So a 3 plus 1 plus 1 plus 1 cycle is how I might say that. Plus 1 plus 1 plus 1. So in other words, this would be just what we would call a 3 cycle. For example, 2, 5, 6 would have this cycle type. This would give me an even permutation because it's just a 3 cycle. Right? So I can write it as a product of 2 transpositions. And its order is just going to be the least common multiple of 3, 1, 1, and 1. In other words, 3. All right, I think we're done with everything that includes a 3 cycle inside of it. So what more can we do? Well, we can also think about 2 cycles. So if I start out with a 2 cycle, and I want to list the rest of my cycle lengths in a non-decreasing fashion, then one cycle type that would be available to me is 2 cycle, composed with 2 cycle, composed with 2 cycle. The cycle type 2 plus 2 plus 2. It's a product of 3 transpositions. Because it's a product of 3 transpositions, we know for sure that it's going to be an odd permutation. We also know for sure that its order is going to be the least common multiple of 2, 2, and 2. Namely, its order is going to be 2. Anytime I have 3 disjoint transpositions, all I'm doing basically is I'm taking 3 light switches and I'm flipping each one of them. Right? None of them affect the others. And if I do that same process once again, I always end up right back where I started. So 2 plus 2 plus 2, that one's an easy one to classify. It also happens to be an odd permutation. All right, what else can we do? Well, we can start out with a 2 cycle composed with a disjoint 2 cycle, but then we can leave the last couple alone. So we can fix the remaining elements. I would call this cycle type 2 plus 2 plus 1 plus 1. So this is a product of 2 transpositions and 2 identity permutations. That makes it an even permutation, but the order is still 2. It's not so bad. All right, home stretch. What else can I do? I can take my first 2 elements and do a transposition on them, but then I can leave everything else absolutely fixed. So I fix one more symbol, I fix one more symbol, I fix one more symbol, and then I fix one more symbol. This cycle type would be 2 plus 1 plus 1 plus 1 plus 1. In other words, this would be just a single transposition inside of S6. It's a single transposition. That makes it an odd permutation. That also makes its order 2. And of course, last but certainly not least, is the cycle type in which everything is fixed. So fix one symbol, fix the second symbol, fix the third symbol, fix the fourth symbol, fix the fifth symbol, and then also fix the sixth symbol. We would call this cycle type 1 plus 1 plus 1 plus 1 plus 1 plus 1. That is the identity permutation. So its order is 1, and it's an even permutation. Blah. All right. We made it all the way to the bottom of our list. Here are all the possible cycle types for permutations inside of S6. All 720 permutations are going to fall into one of these 11 categories. These also happen to be, if you watched our video from the last session on conjugacy classes, these also enumerate the conjugacy classes of elements inside of the symmetric group on 6 symbols. That's a fact that we might need. We might not even need that fact this semester. It becomes something that's super helpful in the second semester of abstract algebra when you end up using the symmetric groups to classify the roots of polynomial equations over the rational numbers, which is super fun, super interesting, and it was my first, really my first YouTube series of video lectures was on that second half of abstract algebra, so I'm a bit partial to it. But the purpose of this problem was to classify all the orders of elements inside of S6. And what we find here is that every element in S6 has order 1, 2, 3, 4, 5, or 6. There's no element inside of S6 that has an order bigger than 6. Even though taken together, all of their combinations with one another form 720 different elements inside of the symmetric group on 6 symbols. So cycle type is a super big deal. And chances are, if I ask you a question on a quiz or an exam that has to do in any way with the order of elements inside of a symmetric group, chances are using cycle type in the way that we used it in this problem is the way to crack the code on those kinds of problems. Let me pause for just a minute here, let everybody get caught up. If you have questions, throw them in Slack, throw them in the Twitch chat. We're going to move on and do one last problem, which involves characterizing a subset of the alternating group as a subgroup or not. All right, so let's move on to our last problem. And this problem is going to be a proof. So let's dig in. I'm going to put my proof glasses on. So for this last problem, I want to assess the following question. So inside of the alternating group on 5 symbols, is this subset a subgroup? So I've written out here a subset using set builder notation. It's the set of all even permutations. So remember, that's what we mean by the alternating group. It's the set of even permutations on 5 symbols. And they're those even permutations that fix the 4th position. So nothing happens to 4 in the process of these permutations acting. So this is a subset of A5. The question is it a subgroup of A5? So first of all, before we go any further, I want us to, again, we're going to want to make an argument about cycle type. If we want to at least get a feel for what's going on in this question, being able to say something about cycle type could be really helpful. So I want to actually skip back to the last screen for just a moment, and let's look together at where is the alternating group in this chart of cycle types. So let's finish up by just highlighting it. So where is A6? A6 is going to consist of all of the even permutations. And evenness and oddness is also a property that is invariant in conjugacy classes. That was just a fancy way of saying the cycle type determines the evenness or oddness of a permutation, and nothing else about that permutation. It doesn't matter which of the symbols are being permuted, it only matters what type the cycle is to determine whether it's even or odd. And that's super great news, because let's see what we can pull out of this table here as far as figuring out what A6 is. Where are my even permutations? Well, my first row here is a row of even permutations. Right, the row of 4 plus 2 cycles. Sorry, my highlighter is a little bit off center. There we go. So the 4 plus 2 cycles definitely count. The 5 plus 1 cycles also count. My grid is a little bit off here, so bear with me for just a second. So my 5 plus 1 cycles will all count. So will my 3 plus 3 cycles. So will my 3 plus 1 plus 1 plus 1 cycles. In other words, my just 3 cycles. So will my 2 plus 2 cycles. And then, of course, there's the last row, which is my identity permutation, my 1, 1, 1, 1, 1, 1 cycle. So there are the cycle types for the alternating group on 6 symbols. Is there anything we can learn about them? Well, it looks, so one conjecture that we might make is if we add up the cycle lengths, that we get an even sum when we have an even permutation and an odd sum when we have an odd permutation. But that doesn't appear to hold, because 4 plus 2 happens to be even, 5 plus 1 is even, 3 plus 3 is even, but 6 and 4 plus 1 plus 1, those are all odd. After all, these are all partitions of 6. So when I add up these cycle lengths, I'm always just going to get the number 6. So that's not good enough. What instead we can look at is the relative parities of the cycles. So here, in this cycle type, both of my permutations are even length, right? A 4 and a 2. Here, both of them are of odd length, 3 and 3. Whereas in these other examples, well, I guess in this example, these all have even length. So maybe we do have to kind of think of these one at a time, right? So under what circumstances am I going to have an even number of transpositions? I'm going to have an even number of transpositions in the case where I'm adding together either an odd number and an odd number of transpositions, or an even and an even number of transpositions. So, for example, in this 4 plus 2 cycle, this 4 cycle is going to be made up of 3 transpositions, the 2 cycle of 1 transposition, and when I add 3 and 1, I get an even. Same thing here with 5 and 1. This 1 becomes a 0, and so this 5 just becomes a 4, and I get an even cycle type as well. So let's try and go one at a time, and if I want to sort of brute force an exploration of this question, whether or not this subset is a subgroup, what I might do in the beginning is I might just try and write out what are all the cycle types of the elements that belong to this subset. So I'm going to think of this as like a brute force way. Let's list all the cycle types. And if we can even list all the cycles. A5 is not a ginormous group. It has 60 elements in it, so it's not as bad as S6 would have been. But this subset is probably going to have a lot fewer than 60 in it. So let's see if we can make some headway by listing out cycle types. So first of all, the cycle type that just fixes every element, 1, 1, 1, 1, 1 in A5. In other words, the identity permutation. That's going to fix position 4. So it definitely is an element of H. All right, what's another cycle type that gives me even permutations? How about 2, 2, 1? This gives me even permutations because it's a product of 2 transpositions, right? So what would an example of a 2, 2, 1 cycle look like? Well, one example would be 1, 2, 3, 5. That's a 2 plus 2 cycle. Right? And notice I've deliberately used 1, 2, 3, and 5 here because I want my permutation also to fix position 4. So nothing is happening to 4 here. In fact, if I want to, I can remind myself by putting this 4 in a little 1 cycle out here at the end. That don't change anything. Is this the only 2 plus 2 cycle that's an element of H? Well, the answer to that is no. There's 2 others. There's 2 other ways to leave 4 in place while permuting 1 and 2. or sorry, permuting 1, 2, 3, and 5 in a 2 plus 2 cycle. I could do 1, 3, 2, 5, and I could do 1, 5, 2, 3. So there are 3 elements that have the 2, 2, 1 cycle type. Those are going to be elements of H. All right, what's the next cycle type? Well, what about a 3 cycle and 2 objects being fixed? Well, that's going to be an even permutation also, because every 3 cycle is the product of 2 transpositions also. And so if I think, first of all, about what my 1 and 1 are going to be, I know one of my fixed elements has to be 4. But my other fixed element doesn't necessarily have to be 4. So if I pick 1, for example, as my fixed element, then I could have a 3 cycle 2, 3, 5 sitting out in the front here. Or I could have the 3 cycle 2, 5, 3 sitting out in the front here. Those are the only possible 3 cycles I can make with the elements 2, 3, and 5. And so there's 2 of my elements. But now I'm going to have a bunch more possibilities, because I could also have chosen 2 to be my other fixed element, and that's going to give me 2 permutations. I could have chosen 3 as my other fixed element. It's going to give me 2 more. I could have also chosen 5 as my other fixed element. It's going to give me 2 more. So I'm not actually being explicit in writing these all out. I'm just trying to make a counting argument here. I've got a total of 1, 2, 3, 4, 5, 6, 7, 8 different elements that have the cycle type 3, 1, 1 inside of A5. So there are 3 elements here that have this cycle type, and there's 1 element that has the identity cycle type. That's always true, of course, because identities are unique. Okay, well, there's one more cycle type that we haven't looked at. It's the cycle type that includes all 5. Notice I skipped over the 4 plus 1 cycle type, because that would be an odd permutation. Just like I skipped over the 2, 1, 1, 1 cycle type, that would be an odd permutation. So when I move up in cycle length, I'm going to move up by 2s if I'm trying to figure out just the even permutation, so the 5 cycle type. Well, there's a problem, though, with the 5 cycle type. Let's say I wanted to write down a 5 cycle. What symbols do I have to put in here? Well, I only have 5 symbols to permute. And no matter which way I write them all down, 4 is going to be one of them. And so all of my 5 cycles are going to move position 4 inside of A5. If we were in A6, we could get away with it. Right? We could put 4 off to the side and then do a 5 cycle on the remaining 5 symbols. But we can't do that here, because we only have 5 symbols to work with. Every 5 cycle doesn't fix 4. And so of this cycle type, there are actually no elements at all in my subset H. So that was kind of a brute force way. What we end up getting is a total of 12 elements in my set H. And if I were so motivated, what I could do is I could verify whether or not this met the criteria of closure, identity, inverse. Notice it meets the associativity criterion automatically because its operation is inherited from the operation of A5, which is a group, and therefore its operation is associative. That was true because it's a subgroup of S5, and the permutations in S5 are defined by function composition, which is by definition associative. Therefore, A5 is a subgroup. Okay, all of that was just to say, let's not check associativity. We would check closure. So we'd have to take any pair of these 12 elements, of which there would be 66 different pairs to check, and check that every pair that I compose together is going to give me another one of these same elements. Check identity, well, that's quick, it's right here. And check inverse, and inverse is actually pretty easy to check. All of these 2 plus 2 cycles are their own inverses. All of these 3 cycles, their inverse is just going to be their second power, because those are going to be elements of order 3. And if we know that their second power is in here because of closure, that means the inverse property is also satisfied. But that is a really clumsy way to verify that a subset is a subgroup. And it's a way that we want to always be able to avoid if we can get away with it. We want to work smarter, not harder. So if I want to come up with an actual proof, let's think about what my option would be. If we're sort of got the hunch that this is a subgroup, let's use one of our subgroup tests. And because A5 is a finite group, it's finite because its parent group S5 is also finite, we can use the finite subgroup test. And the great part about the finite subgroup test is that it's a theorem that tells me that for finite subsets of a group, the only property that we need to verify that it's a subgroup is closure. If we verify closure, then inside of a finite group, inverse property and identity property are automatically satisfied. So let's just verify closure, which is to say, if I have a sigma and a tau that are both elements of H, in other words, if they both fix the element 4, does their composition also fix the element 4? Well, that would seem to make a whole lot of sense. If sigma doesn't touch position 4, and tau doesn't touch position 4, then when I compose sigma tau with one another, sigma tau applied to 4 means, by function composition, that first tau is going to act on 4, which means it doesn't move 4 because tau fixes 4. So it's going to pass 4 over to sigma, which is also not going to touch 4 because sigma fixes 4. So there's my napkin version of this proof. Let's structure it into a full proof. So first thing in my proof is I want to give away my strategy. We're going to use the finite subgroup test, which is possible since A5 is a finite group. What's my burden of proof? My burden of proof is we just need to show the closure property holds for this subset H. And to rephrase that burden of proof, to remind the reader of what closure is, what it looks like, we need to show for all sigma and tau in the subset H, the composition, using the operation of the symmetric group, is also an element of H. So, because we're supposed to substantiate a universal claim, the first thing that we need to do is arbitrarily choose, and by we, I mean the universe, needs to arbitrarily choose 2 elements of the subset H. So the universe is coming along and picking 1 and 2 of these 12 elements all out of a hat with replacement, right? We could choose the same element twice. The universe doesn't care. It's picking 2 arbitrary elements of H, which are listed over here on this side. Let me cross out this 5 cycle just to remind us that that's actually not there. It's going to be one of the 12 that's listed on that side. Let sigma and tau be arbitrarily chosen. What's going to happen when I do sigma compose with tau? Well, by definition of the subset H, right, the definition is right up here, right? By definition of the subset H, sigma has the property that it fixes position 4. So sigma of 4 is equal to 4. Also, because tau belongs to H, tau has the property that it fixes position 4. Tau of 4 is equal to 4. How do we prove that sigma composed with tau belongs to H? Well, that means we need to show that sigma composed with tau fixes position 4. We should probably also remind ourselves why sigma tau remains an element of A5. Well, fixing position 4 is the interesting part of this proof, and it's where we can put this bar napkin logic into our proof. Sigma tau applied to 4 means the permutation sigma applied to the output of tau applied to 4. But by definition, tau of 4 is equal to 4, and therefore sigma of tau of 4 is the same as sigma of 4. But by definition of H, sigma also fixes 4, so sigma of 4 is equal to 4. Reading this from left to right, this shows that sigma tau of 4 is equal to 4. Therefore, sigma tau fixes position 4, so sigma tau belongs to the subset H. Let's just finish by making the observation. And depending on the audience reading your proof, this may be a necessary thing to observe. It may not. But since we're still getting used to this stuff, let's remind ourselves. Not only does sigma tau fix position 4, it also satisfies the first criteria for membership inside of the subset H. It's an element of A5. Why? Because sigma tau is even. It's even because it's the composition of an even permutation with another even permutation. And even composed with even is even. Another way to express this is we know that A5 is closed under the operation of the group. Why? Because we know A5 is a subgroup. We've already proved that A5 is a subgroup of S5. Therefore, it has the closure property itself. So sigma tau is going to remain in A5 as well. So this subset of A5 actually does end up being a subgroup of A5, which we just proved using the finite subgroup test. And I want to just close by making the following observation. So we just showed that this, in fact, is a subgroup of A5. And here's my last observation. This is a group that has 12 elements, 8 that have this cycle type, 3 that have that cycle type, 1 that has that cycle type. It turns out and we'll be able to make this more concrete in our next chapter. It turns out that H is the same as the group A4, which I think you can convince yourself of as follows. By insisting that all of the elements in H don't touch position 4, that really means that we only have 4 elements to work with, 1, 2, 3, and 5. And any even permutation of 1, 2, 3, and 5 is going to be an even permutation of 1, 2, 3, 4, and 5. But it's also going to be the same as an even permutation of just 4 symbols, where we call the symbols 1, 2, 3, and 5 at the end of the day. We're going to be able to make this notion of sameness concrete in our next chapter. Before we wrap up the stream, let me address the question that just popped up, which is, in this example, H was defined by fixing an element. What if we defined this subset in a different way, where instead of fixing an element, we insist on moving it? So what if we think of the set of permutations that moves 4 to 2, for example? Moving 4 to 2. And the questioner has actually already answered their own question inside of the question, which are the best kinds of questions sometimes. But would this be a subgroup? And the answer would have to be no. And the answer is no for a variety of reasons. But probably the quickest way to understand why the answer would be no is to observe that the identity permutation would not belong to this subset, right? And it doesn't belong to the subset because the identity permutation does not move 4 to position 2. Because after all, it doesn't move any position to any other position. So this would fail the identity property. It would also fail the inverse property, because not every permutation that moves 4 to 2 will have an inverse that moves 4 to 2 as well. I think the only one that does is going to be that which has the transposition 2-4 as one of its disjoint factors. So that would fail. Also, the closure property. We could pretty simply, I think, take 2 permutations that move 4 to 2, compose them together, and get something which no longer moves 4 to 2. For example, even just the transposition 2-4. That's an element of this subset, but when I compose it even with itself, I'm going to get the identity, and the identity is not an element of this subset. So, Colleen, that's right. Whoops, I didn't type in the right place here. That's right. There we go. So yeah, one of the things that we kind of learned from this is if we're looking inside of the symmetric group to define a subgroup by the property of, which elements does it move where, really kind of the only option that we have in order to even meet the identity property threshold for that subset is to define it in terms of fixing certain elements. And as soon as I define it only in terms of fixing certain elements, then it turns out that it will end up being a subgroup. And in fact, it'll be a subgroup that's the same as a symmetric group or an alternating group that's acting on fewer symbols. So that's it for today's live stream. If you watch this later on today or before tomorrow's quiz and you have other questions about what we did, feel free to either drop them in Slack. That's probably the best place so that people will see them quickly. Or you can also drop them into the Twitch stream as you're watching the video afterwards as well. I will see you all tomorrow for the quiz, and happy homework and studying between now and then.